Close your eyes for a moment and picture a universe unlike anything you've ever known. A world without stars, without galaxies, without even a single flicker of light. Just an endless, silent expanse of darkness stretching in every direction. This wasn't some far-off corner of space. This was our universe more than 13 billion years ago, in a time scientists call the cosmic dark ages. The very idea feels almost impossible, doesn't it? A cosmos where nothing shone, where the night wasn't just dark but perfectly dark. And yet, this eerie silence held the seeds of everything we see today. The glittering stars, the swirling galaxies, even the atoms that make up you and me. So how did we go from that infinite blackness to the radiant universe we know now? That's the mystery we're about to unravel, and the story is more thrilling than any sci-fi epic. Think about the sheer scale of it, a darkness so complete it lasted for millions of years. No sunrises, no constellations, no faint glow of distant celestial bodies. Just hydrogen and helium drifting through the void, waiting for gravity to pull them into the first fragile structures that would one day become stars. It's a chapter of cosmic history so remote, so alien, that even our most powerful telescopes strain to glimpse its echoes. But those echoes are there, hidden in the faint whispers of radiation left over from the Big Bang itself. And what they tell us is nothing short of miraculous. This era of darkness wasn't an ending, it was a beginning. The universe was gathering its strength, preparing for the moment when light would finally pierce the shadows and rewrite the story of everything. That moment, the dawn of the first stars, changed the cosmos forever. It was the birth of light itself, the spark that ignited the universe as we know it. And here's the most mind-bending part. We're only just beginning to understand how it happened. Cutting-edge telescopes and supercomputer simulations are peeling back the layers of time, revealing how those first stars tore through the darkness, how they forged the elements that make life possible, and how they set the stage for the dazzling cosmic tapestry we see today. This isn't just a story about the past. It's a story about us, about how the universe fought its way out of the shadows to create the conditions that allowed you and me to exist. So let's step into that darkness together and discover how the first light of creation changed everything. To understand how the universe plunged into darkness, we have to rewind even further, back to the very beginning. Picture the Big Bang not as an explosion in space, but as the sudden expansion of space itself, a fiery birth where all matter, energy, and even time burst into existence in a single instant. In those first fleeting moments, the cosmos was unimaginably hot, a seething plasma so dense that light couldn't even travel through it. Particles collided, fused, and vanished in a chaotic dance, as if the universe was a pot boiling over with raw ingredients. But then, something remarkable happened. As space expanded, it cooled. Within minutes, protons and neutrons began to stick together, forming the first atomic nuclei. Mostly hydrogen and helium, the simplest building blocks of everything to come. Think about that for a second. The entire periodic table, all the complexity we see today, started with just two elements. But here's the catch. For hundreds of thousands of years, the universe remained too hot for atoms to fully form. Electrons zipped around freely, scattering light like fog, obscuring a street lamp. It wasn't until the cosmos cooled enough, dropping to a few thousand degrees, that electrons finally settled into orbit around nuclei, completing the first true atoms. And in that moment, the fog lifted. Light, which had been trapped since the beginning, could suddenly travel freely. This is the light we now detect as the cosmic microwave background, the oldest photograph of the universe, a snapshot of its infancy. Yet this newfound transparency came with a twist. With atoms stable and light finally unleashed, the universe had no stars, no galaxies, nothing to make new light. So as space kept expanding, that initial glow faded, stretched into longer and longer wavelengths, and the cosmos slipped into darkness. The particles were there, the potential was there, but without a spark, the universe entered its long cosmic night. And in that stillness, gravity began its slow work, tugging ever so gently at those clouds of hydrogen, setting the stage for the first stars to ignite. The universe was still just a baby, barely 380,000 years old, when something extraordinary happened. It finally caught its breath. After the frenzied chaos of the Big Bang, after eons of particles smashing together in that searing primordial soup, the cosmos had cooled enough for a fundamental shift. The temperature dropped to a mere few thousand degrees, and suddenly, electrons could no longer resist the pull of atomic nuclei. Hydrogen, the simplest and most abundant element, began to take shape, single protons now paired with single electrons, forming stable atoms for the very first time. Helium, too, emerged from the chaos, its nuclei capturing electrons to complete their structure. This moment, known as recombination, wasn't just a quiet chemical process, it was a cosmic revelation. Before this, the universe had been a thick, opaque fog, with free electrons scattering photons in every direction. Light couldn't travel more than a tiny fraction of a second before being deflected, trapped in a perpetual game of pinball. But once those electrons settled into atoms, the haze lifted. Photons, the particles of light, could finally stream freely through space. The universe, for the first time, became transparent. Imagine the scene: a cosmos suddenly flooded with light, a glow stretching in every direction. That light, now detectable as the cosmic microwave background, is like a fossilized echo of that pivotal moment. It's the oldest light we can observe, a snapshot of the infant universe, its patterns encoding the seeds of all future structure. But here's the paradox: while light could now travel freely, there was nothing new to produce it. The universe had cleared the fog, only to reveal an unimaginable emptiness. No stars, no galaxies, just vast, silent oceans of hydrogen and helium drifting in the dark. This transparency came with a cost. As space continued to expand, those first photons were stretched, their wavelengths growing longer and longer, shifting from visible light to microwave radiation. The glow faded, reddening into near-invisible whispers, and so the universe entered its long sleep. The cosmic dark ages where matter existed, but light, as we know it, did not. Yet within that darkness, gravity was already at work, tugging ever so slightly at those primordial gas clouds, setting the stage for the next great act, the birth of the first stars. The cosmic dark ages weren't just a chapter in the universe's history. They were an era of profound stillness, a time when the cosmos held its breath. Lasting roughly 100 million years, this was the gap between the fading afterglow of the Big Bang and the moment the first stars sparked to life. Picture a universe where hydrogen and helium drifted like ghosts through an endless void, where no light pierced the darkness and where silence stretched across billions of light years. No stars meant no starlight, no planets, no cosmic beacons to break the monotony. Even the microwave background radiation, that faint echo of recombination, had stretched into near nothingness, leaving the universe colder and darker than we can fathom. This wasn't merely an absence of light, it was a total reset, a blank canvas waiting for gravity's brushstrokes. Without stars, there were no heavy elements, no carbon or oxygen, nothing but the barest ingredients of existence. And without light, there was no way to see the universe's structure taking shape. If you could somehow travel back to this time, your eyes would perceive nothing, not because of distance, but because there was literally nothing emitting visible light anywhere in existence. The cosmos wasn't empty, though. Those primordial gas clouds were there, moving invisibly, pulled by the faintest tugs of gravity, slowly knitting themselves into denser knots. But here's what makes this era so pivotal. That darkness wasn't static. Every second, gravity was at work, amplifying tiny fluctuations left over from the Big Bang, regions where matter was ever so slightly denser. Over millions of years, these pockets grew, drawing in more gas, building pressure, heating up until finally, deep in those collapsing clouds, the temperatures and pressures crossed a threshold no atom had ever reached before. The universe was about to wake up. The cosmic dark ages were ending, not with a whimper, but with the birth of something revolutionary, the first starlight. And when that light finally pierced the gloom, it didn't just illuminate the cosmos, it transformed it forever. The universe during the cosmic dark ages was a place of almost unimaginable stillness, a vast, unbroken expanse where temperatures plunged to just a few dozen degrees above absolute zero. No stars meant no warmth, no flicker of heat to disrupt the cold. The only matter was neutral hydrogen gas, drifting in featureless clouds so diffuse that a single cubic centimeter of space might contain just one or two atoms. Compare that to the air you're breathing right now, which packs trillions of times more particles into the same tiny volume. This was a cosmos so empty, so achingly sparse, that if you could somehow stand in it, your voice wouldn't even carry. There'd be nothing for sound waves to bounce off, no medium to transmit the vibrations. Just silence stretching into infinity, yet within that apparent nothingness, the universe was far from idle. Those faint ripples in density left over from the Big Bang regions where matter was ever so slightly more concentrated were becoming gravity's fingerprints. Imagine drawing dots on a balloon, then inflating it. The dots don't just move apart, the spaces between them stretch too. Now picture those dots as pockets of gas, and gravity as an invisible hand gently squeezing them together over millions of years. The process was agonizingly slow by human standards, but unstoppable. Hydrogen atoms, pulled by their own minuscule weight, began collapsing into denser knots where pressure mounted and temperatures crept upward. Still, no light emerged. The gas remained dark, neutral, invisible, a cosmic canvas waiting for its first brushstroke of brilliance. What's astonishing is how fragile this equilibrium was. Without the heavier elements we take for granted today, carbon, oxygen, silicon, there were no dust grains to help gas cool efficiently, no complex molecules to radiate heat away. Just pure hydrogen and helium stubbornly holding onto their energy. That's why the first stars took so long to ignite. The gas had to compress until it was hot enough to overcome its own resistance. And when that finally happened, it didn't just create light. It unleashed a chain reaction that would forge the very elements that make up our world. Until then, the universe remained trapped in its quiet, frigid twilight, a place where time itself seemed to hold its breath. Hidden in the darkness of the cosmic dark ages was an invisible architect shaping the destiny of the universe, dark matter. While ordinary hydrogen and helium drifted aimlessly, this mysterious substance, undetectable by light yet outweighing visible matter 5-to-1, was already weaving the cosmic web. Picture a vast, unseen skeleton stretching across the emptiness, its gravitational pull gently guiding gas into the first dense structures. Without dark matter, the universe might have remained a featureless sea of atoms, never clumping together enough to ignite the first stars. The key lies in dark matter's unique properties. Unlike normal matter, it doesn't absorb, emit, or scatter light, hence its name. It doesn't collide with atoms or compress like gas. Instead, it moves through the cosmos like a ghost, feeling only gravity's pull. During the Dark Ages, this meant dark matter could collapse into dense halos long before ordinary matter could overcome its own resistance. These halos became gravitational wells, invisible traps that slowly funneled hydrogen inward. Over millions of years, gas accumulated in their depths, growing hotter and denser until the conditions for star birth were finally met. Here's the twist. Dark matter didn't just assist, it dictated the universe's blueprint. Computer simulations reveal how its tendrils formed an intricate network, a cosmic highway system where gas flowed into intersections, creating the first proto-galaxies. The largest dark matter halos anchored the future sites of massive galaxy clusters, while smaller ones seeded individual stars. Even now, the galaxies we observe align along these ancient filaments, tracing patterns set in motion during the Dark Ages. Yet dark matter's influence came with a paradox. Its dominance meant the first stars formed differently than those today. Without heavy elements to help gas cool, collapse, and fragment, early star-forming clouds had to grow far more massive before igniting. This likely produced dazzling, short-lived giants hundreds of times heavier than our Sun, blazing brilliantly before exploding as supernova. Those cataclysms, in turn, enriched the cosmos with the first heavy elements, setting the stage for everything that followed: planets, life, even us. So while the Dark Ages seemed empty, dark matter was the unseen hand molding the universe, orchestrating the transition from darkness to light. Its gravitational whispers turned chaos into structure, ensuring that when starlight finally pierced the void, it didn't just illuminate, it revealed a cosmos already pregnant with possibility. Even before the universe slipped into its long cosmic night, the seeds of structure were already planted: tiny ripples in the fabric of space itself. These weren't grand cosmic waves, but whisper-thin variations in density, regions where matter was ever so slightly more packed together than the surrounding emptiness. Imagine blowing gently on the surface of a still pond. The ripples you create are faint, barely noticeable, yet they spread outward, shaping the water's motion. Now picture those ripples not in water, but in the newborn universe, imprinted during the Big Bang's first trillionth of a second. At first, these fluctuations were absurdly small, density differences of just 1 part in 100,000. To put that in perspective, if the early universe had been a perfectly smooth sheet of glass, these imperfections would have been no thicker than a single grain of sand sprinkled across a football field. Yet gravity, patient and relentless, seized on even these minute variations. Wherever matter was slightly denser, gravity pulled a little harder, drawing in nearby gas with an imperceptible but unyielding tug. Over millions of years, what began as microscopic wrinkles grew into vast cosmic scaffoldings, the first threads of the universe's grand tapestry. Here's where things get fascinating. Without turbulence or collisions to disrupt them, these early gas clouds didn't clump randomly. Instead, they followed the invisible framework of dark matter, flowing along its gravitational contours like water trickling down a hillside. As hydrogen and helium pooled in these deepening wells, the gas grew hotter and denser, swirling into flattened disks, protogalactic nurseries where the first stars would soon ignite. But these weren't the majestic spiral galaxies we recognize today. The earliest structures were messy, chaotic affairs, often no larger than 1/100th the size of our Milky Way. Gravity worked with what it had, sculpting them into rough, irregular shapes rather than the elegant pinwheels we see now. And because the universe was still so small and dense, these protogalaxies frequently collided, merging into larger and larger structures in a slow-motion dance that continues to this day. What's truly mind-bending is how fragile this process was. If those initial density fluctuations had been even slightly weaker, gravity might never have gathered enough material to spark the first stars. Too strong, and matter could have collapsed into monstrous black holes before starlight had a chance to shine. Instead, the universe struck a perfect balance, just enough variation to create structure, but not so much that it tore itself apart. And hidden within those first clumsy knots of gas lay the blueprint for everything to come: galaxies, planets, and ultimately us. So when we gaze at the night sky today, we're not just seeing stars, we're witnessing the amplified echoes of those quantum ripples from the dawn of time. The same gravitational forces that first stirred the cosmic dark ages are still at work, shaping galaxies billions of years later. It's a reminder that even in the emptiest reaches of space, nothing is ever truly still. The universe is always becoming, always building, one invisible tug at a time. Deep in the heart of the cosmic dark ages, something extraordinary was brewing, a revolution that would shatter the silence forever. The universe, cold and dark for millions of years, was finally ready to ignite its first stars. But these weren't just any stars, they were cosmic pioneers blazing into existence under conditions so extreme they would make modern supernova look tame. Picture a star not just bigger than our Sun, but hundreds of times more massive, burning at temperatures so fierce they could fuse hydrogen in seconds rather than millennia. These were the universe's first light bulbs, flickering on one by one in the void, ending the Dark Ages with a brilliance we can barely comprehend. Yet despite their monumental importance, these stars remain ghostly figures in our telescopes. Why? Because they lived fast and died young, exploding in catastrophic supernova before most galaxies even began to form. Their light, stretched by 13 billion years of cosmic expansion, now reaches us as faint infrared whispers, signals so dim they're drowned out by the glow of younger, closer stars. It's like trying to spot a single candle flame on the other side of a roaring bonfire. Even our most advanced observatories, like the James Webb Space Telescope, strain to pick out their signatures from the noise of the universe. Compounding the challenge is how differently these stars formed. Today's stars are born in clouds laced with heavy elements, carbon, oxygen, iron, that help gas cool and collapse efficiently. But the first stars had none of that. They emerged from pure hydrogen and helium, which resisted compression until gravity forced it into incredibly dense, hot cores. This meant they likely grew far larger than any star we've ever observed, some possibly reaching 1,000 times the mass of our Sun. Their sheer size made them unstable, burning through their fuel in just a few million years before erupting in titanic explosions that seeded the cosmos with the first heavy elements. These explosions weren't just fireworks, they were the universe's first alchemists, forging carbon, nitrogen, and oxygen in their cores and scattering them across space. Without those elements, later stars could never have formed rocky planets or the molecules essential for life. So while we may never directly see those first stellar giants, their legacy is written in everything around us, from the iron in our blood to the silicon in our smartphones. They didn't just end the Dark Ages, they laid the foundation for the universe we call home. And here's the tantalizing part, we might be on the verge of glimpsing them at last. New telescopes are peeling back the layers of time, searching for the unique chemical fingerprints those first stars left behind. Some theories even suggest a few might still survive in the farthest reaches of space, frozen in time like cosmic relics. Whether we find them or not, their story reminds us that even in the deepest darkness, light and life always finds a way. Within the endless blackness of the cosmic Dark Ages, an invisible chemical ballet was unfolding, one that would determine how and when the first stars could form. While the universe seemed frozen in time, the simplest molecules were beginning to emerge from the primordial fog. Hydrogen atoms, the most abundant building blocks of existence, started pairing up in the cold void, forming fragile hydrogen molecules, just two protons bound together by a shared electron. This delicate dance wasn't just a curiosity, it was the universe's first step toward building something greater. Here's why these molecules mattered. They acted as cosmic radiators. When a hydrogen atom collides with another, the energy often sends them ricocheting apart. But when two hydrogen atoms form a molecule, that collision energy can be released as infrared light, carrying heat away into space. This subtle cooling effect was like opening a vent in a stifling room. It allowed vast clouds of gas to shed energy, contract, and eventually ignite under gravity's pull. Without this molecular cooling, the gas might have remained too hot and diffused to ever collapse into stars. The process was achingly slow. In the near-perfect vacuum of the early universe, atoms might wander for millions of years before finding a partner. But when they did, the consequences were profound. These molecules became the universe's first thermostats, regulating the temperature of star-forming regions with surprising precision. As hydrogen gas grew denser in dark matter's gravitational wells, Molecules helped it shed just enough heat to keep collapsing, not so fast that it fragmented chaotically, not so slow that it stalled entirely. There's a beautiful irony here. The same darkness that made this era seem lifeless was actually its greatest ally. With no starlight to rip molecules apart, they could survive long enough to work their cooling magic. Compare that to today's universe, where fierce UV radiation from stars breaks apart most hydrogen molecules before they can influence gas clouds. Back then, the darkness wasn't an obstacle, it was the perfect laboratory for cosmic chemistry. Yet hydrogen molecules had limits. Unlike modern star-forming clouds enriched with carbon and oxygen, which can cool to just a few degrees above absolute zero, primordial gas could only chill to around 200 degrees Celsius, still scorching by earthly standards. This meant the first stars had to form under extreme pressure, packing far more mass into a single object than typical stars today. It's why many astrophysicists believe the universe's first light came not from modest suns like our own, but from behemoths that burned blue hot and died young, scattering the first heavy elements into the void. This molecular alchemy didn't just shape stars, it set the rhythm for cosmic evolution. The efficiency of cooling determined how quickly gas could collapse, how massive stars could grow, and even how soon galaxies might assemble. Invisible and silent, these hydrogen molecules were the unsung architects of light, quietly laying the groundwork for the universe's dazzling future. And when those first stars finally ignited, their radiation would break apart countless molecules, ending the Dark Ages not just with light, but with a chemical revolution that echoes through the cosmos to this day. If we could rewind the universe back to that moment just before the cosmic Dark Ages began, we'd find ourselves staring at a wall of light, not the shimmering starlight we know today, but something far more primal. This is the cosmic microwave background, or CMB, the oldest light in existence, a fading echo of the Big Bang itself. Picture it like the glow of a campfire long after the flames have died, cooling embers still radiating heat into the night. Except in this case, the fire was the birth of the cosmos, and those embers have been stretching across space for over 13 billion years. What makes the CMB so extraordinary is that it's not just ancient light, it's a literal photograph of the infant universe frozen in time. When that light first broke free during recombination, the universe was a near-perfect soup of hydrogen and helium, with only the tiniest variations in density. Those microscopic ripples, smaller than 1 part in 100,000, are imprinted on the CMB like fingerprints. Today, we can map those fluctuations with satellites like Planck and WMAP, revealing a universe that was already, even in its infancy, subtly lumpy. And those lumps, those faint, ghostly irregularities, were the seeds of everything to come. Here's the profound connection. The CMB marks the exact moment the cosmic Dark Ages began. As the universe expanded, that initial light stretched from visible wavelengths into microwaves, fading from a brilliant glow to a whisper. But crucially, it also captured the state of the cosmos just before darkness fell. It's like finding a fossilized bubble in amber, a pristine snapshot of conditions right before gravity began sculpting the first structures. The denser regions in the CMB correspond to where dark matter would later pull in gas, forming the first protogalaxies. The emptier patches, those became the great cosmic voids. Yet the CMB doesn't just show us the past, it helps explain why the Dark Ages ended. Without those initial density variations, gravity would have had nothing to work with, and the universe might have remained a featureless sea of gas forever. Instead, the slight overdensities we see in the CMB acted like cosmic breadcrumbs, guiding matter into the gravitational wells that birthed the first stars. It's a staggering thought. The blueprint for today's glittering cosmos was encoded in those microwaves long before even a single star had ignited. What's equally remarkable is how uniform the CMB appears at first glance. Across the entire sky, its temperature varies by less than 0.1%, proof of how smooth and homogeneous the early universe was. But look closer, and those tiny fluctuations tell a different story. They're the universe's first murmurs of structure, the faint static that would one day crescendo into galaxies. And because the CMB comes from a time before stars or dust could distort it, it remains the cleanest window we have into the cosmos's origins. Modern telescopes have turned this afterglow into a Rosetta Stone for cosmologists. By studying its patterns, we've calculated the universe's age, confirmed the existence of dark matter, and even glimpsed hints of cosmic inflation. That explosive expansion in the first fraction of a second after the Big Bang. But perhaps its most poetic role is bridging two eras. It's the last light of the fireball universe and the first herald of the darkness to come. When we observe the CMB, we're not just seeing where we came from, we're witnessing the quiet before the dawn. Imagine pointing the most powerful telescope in history toward the cosmic dark ages and seeing absolutely nothing. No swirls of distant galaxies, no pinpricks of starlight, not even the faintest glimmer of infrared warmth. Just an impenetrable curtain of blackness stretching across billions of light years. This isn't a limitation of our technology, it's the defining feature of that epoch. Unlike every other era in cosmic history, the Dark Ages left no electromagnetic signature for us to detect. No radio waves, no X-rays, no visible light. The universe wasn't just dark, it was for all intents and purposes invisible. To understand why, think about how telescopes usually work. Whether they're capturing starlight, the glow of nebulae, or the shimmer of quasar jets, they're all detecting photons, particles of light emitted by energetic processes in space. But during the Dark Ages, there were no stars to blaze, no black holes to fling out radiation, no cosmic collisions to spark bursts of energy. The only photons in existence were those from the cosmic microwave background, and by this time they'd stretched into feeble microwaves, carrying no information about the universe's structure. Meanwhile, the neutral hydrogen gas drifting through space couldn't emit or absorb light efficiently. It was like a vast, silent ocean with no lighthouses, no buoys, nothing to break the monotony. This silence creates a paradox for astronomers. We can study the universe before the Dark Ages thanks to the CMB, and after thanks to galaxies and quasars, but the era itself. It's a blind spot, a cosmic missing link. Traditional telescopes hit a wall because they rely on electromagnetic signals, and the Dark Ages offered none. Even the James Webb Space Telescope, designed to peer back to the universe's infancy, can't penetrate this void directly. Its infrared eyes are tuned to spot the earliest galaxies, but those didn't form until after the Dark Ages ended. Yet scientists haven't given up. If light won't reveal this era, maybe something else will, like sound. Not literal sound, of course. Space is a vacuum after all, but pressure waves rippling through the primordial gas. In those first few 100,000 years after recombination, the universe was still dense enough for sound to travel, creating faint vibrations as matter clumped under gravity's pull. These waves left subtle imprints on the distribution of hydrogen, like fossilized echoes waiting to be decoded. Here's where ingenuity comes in. Radio astronomers are now hunting for a specific signal. The moment ultraviolet light from the first stars began splitting neutral hydrogen atoms apart, a process called reionization. This event marked the end of the Dark Ages, and the radiation it released should have left a faint fingerprint in the hydrogen gas, a signal at the specific wavelength of 21 centimeters. Catching this whisper would be like finding a recording of the universe's first dawn, a direct probe into the darkness. But there's a catch. This signal is buried under a cacophony of interference from modern galaxies, cosmic rays, even Earth's own radio chatter. It's like trying to hear a single note of a flute in the middle of a thunderstorm. Projects like the Square Kilometre Array and the Hydrogen Epoch of Reionization Array are racing to isolate this signal, using vast fields of antennas to filter out the noise. If they succeed, they'll effectively turn the cosmic dark ages from an impenetrable void into a readable chapter, a way to see an era where light itself went silent. Until then, this period remains the universe's greatest disappearing act, a reminder that sometimes the most pivotal moments leave the faintest traces. To piece together the mysteries of the cosmic dark ages, a period hidden from even our most advanced telescopes, scientists have turned to the digital realm, constructing entire universes inside supercomputers. These aren't just abstract sketches, they're hyper-detailed simulations that account for everything from the faintest gravitational tugs to the quantum behavior of primordial gas. Imagine building a virtual cosmos from scratch, programming in the laws of physics, then hitting play to watch billions of years unfold in days. The results are breathtaking, swirling clouds of hydrogen coalescing into the first protogalaxies, dark matter weaving invisible scaffolding, and the explosive birth of stars that shattered the eternal night. One of the most groundbreaking tools in this cosmic detective work is the Renaissance simulation, a computational marvel that zooms in on key moments during the Dark Ages with unprecedented precision. Unlike traditional models that treat gas as a smooth fluid, Renaissance tracks individual parcels of matter, revealing how microscopic turbulence and shockwaves influenced star formation. The simulations suggest something astonishing: the first stars didn't ignite in isolation. Instead, they likely erupted in clusters, their collective ultraviolet radiation tearing through neighboring gas clouds like a chain reaction, sparking secondary waves of star birth. This challenges the old assumption that early starlight flickered on sporadically, painting a far more dynamic picture of the cosmos awakening. But crafting these models isn't just about raw computing power. It's a delicate balancing act between known physics and educated guesswork. Take the role of dark matter. While we can't directly observe it, simulations incorporate its gravitational influence by tweaking parameters until virtual galaxies match the few clues we can see, like the distribution of ancient hydrogen revealed by quasar light. Sometimes the models surprise us. Recent runs from the Fire project showed that the first stars may have formed earlier than thought, in mini-halos barely 1/1,000,000th the Milky Way's mass. If confirmed, this would compress the timeline of the Dark Ages, suggesting the universe woke up faster than we ever imagined. The stakes for these simulations couldn't be higher. They're our only window into an era that shaped everything that followed. The distribution of galaxies, the creation of heavy elements, even the conditions for life. And as telescopes like JWST spot galaxies from shockingly early times, their data is fed back into simulations, refining the virtual cosmos again and again. It's a feedback loop between digital prophecy and real-world observation, each sharpening the other. What's emerging is a story of chaos and ingenuity. The Dark Ages weren't a static pause but a seething cauldron of potential, where the tiniest fluctuations snowballed into cosmic landmarks. And while we may never observe this era directly, these digital universes let us walk through it like archaeologists reconstructing a lost civilization, one line of code at a time. Hidden in the faint whispers of the cosmos lies a signal so delicate, it carries the fingerprints of the universe's darkest era, the 21-centimeter line. This isn't just any wavelength, it's a direct echo of the primordial hydrogen that once filled the universe during the cosmic dark ages, a tuning fork vibrating at the exact frequency of nature's simplest atom. When neutral hydrogen's solitary electron flips its spin, it releases a photon with a wavelength of 21 centimeters, a radio whisper that could, if we can catch it, map the distribution of gas before the first stars even formed. Detecting this signal is like trying to listen for a single raindrop in a hurricane. The challenge isn't just its faintness. After 13 billion years of cosmic expansion, that original radio wave has stretched to meters in length, its energy diluted to a billionth of its initial strength. What's worse, it's buried under a cacophony of noise, the roar of our own galaxy's synchrotron radiation, the buzz of earthly radio stations, even the static from satellites cluttering the sky. Separating the 21-centimeter signal from this chaos is like picking out a conversation at a rock concert while wearing earplugs, yet the payoff would rewrite cosmic history. Unlike the cosmic microwave background, which shows us the universe as a newborn, the 21-centimeter line could reveal its awkward adolescence, the turbulent phase when gas first began clustering under gravity's pull. By mapping how this signal varies across the sky, astronomers could trace the invisible scaffolding of dark matter, watch the first proto-galaxies assemble, and pinpoint the exact moment when starlight began tearing hydrogen atoms apart during reionization. It's a time lapse of the universe waking up frame by frame. To catch this ghostly signal, scientists are building telescopes unlike any before. Projects like the Hydrogen Epoch of Reionization Array and the Future Square Kilometer Array use thousands of simple radio antennas spread across deserts and remote plains, their combined power creating a virtual dish the size of a continent. These arrays don't just listen for the 21-centimeter line, they hunt for its absence. During the Dark Ages, regions where gas was denser should appear slightly darker in this radio light, having absorbed more background radiation. These shadows, subtle as they are, could reveal the universe's first structures in startling detail. But here's the twist: the signal isn't just weak, it's warped. As the universe expanded, the 21-centimeter line from earlier epochs stretched to longer wavelengths, meaning the deeper we listen, the more the signal shifts. Early results from telescopes like EDGES have sparked controversy, with some claiming to detect a surprisingly strong signal that could hint at unknown physics, perhaps interactions between dark matter and hydrogen. Others remain skeptical, arguing the data could still be contaminated by earthly interference. The quest for the 21-centimeter line is more than technical, it's philosophical. If successful, we'll have unlocked a direct window into an era without light, watching gravity's patient work in real time. And buried in those radio murmurs might be answers to even grander questions. Was star formation slower or faster than we thought? Did dark matter behave strangely in those early epochs? Could there have been exotic particles shaping the gas we've never detected? Every failed attempt sharpens our tools. Every tentative detection rewrites our expectations. What makes this search so thrilling is its universality. That faint hydrogen line connects us directly to the cosmic dark ages, a time when everything, every atom in our bodies, every star we gaze at, was just a wisp of gas waiting in the dark. And when we finally tune into that elusive signal, it won't just fill a gap in our knowledge, it'll let us hear the universe's first heartbeat. The farthest edges of the observable universe aren't just a distant place, they're a distant time, a frontier where the limits of our vision collide with the mysteries of the cosmic dark ages. No matter how powerful our telescopes grow, there's an ultimate horizon we can't see beyond, not because space ends, but because the universe was once opaque. Imagine standing in a thick fog where visibility drops to zero. That's what the era before the first starlight looks like to astronomers. The cosmic microwave background gives us a snapshot from 380,000 years after the Big Bang, and the earliest galaxies show us what came hundreds of millions of years later. But the Dark Ages, they're the missing reel in the cosmic film, a gap where the universe left no light for us to catch. This isn't just about distance, it's about a fundamental shift in how the universe behaved. During those primordial epochs, neutral hydrogen gas acted like a cosmic fog, absorbing any radiation trying to pass through. Even if stars had ignited earlier, their light would have been swallowed before it could travel far. The result, a literal wall blocking our view, cutting us off from nearly everything that happened in the first half-billion years after the Big Bang. Telescopes like Hubble or JWST can peer back to galaxies within 400 million years of cosmic dawn, but push further and the curtain falls. That unseen expanse holds answers to profound questions. Did structures form differently in those first moments? Were the laws of physics the same? Could there have been exotic phenomena we've never imagined? What makes this era such a tantalizing frontier is how it forces us to rethink observation itself. Normally, astronomers rely on light to map the cosmos, but when light can't escape, we have to get creative. Some teams hunt for gravitational waves, ripples in space-time that might carry echoes from the universe's birth, unaffected by the fog. Others simulate the dark ages in supercomputers, reconstructing possible scenarios from the faintest clues. And then there's the 21-centimeter radio signal, a potential backdoor into this hidden epoch if we can tease it from the noise. Each approach is like feeling the outline of an object in the dark, guessing its shape from indirect clues. The irony is that this blind spot might hold the keys to our cosmic origins. The way gas clustered during the Dark Ages set the stage for all future structure, determining where galaxies would bloom and where vast voids would stretch. Without understanding this era, we're missing the first act of the universe's story, the part where the script was written. That's why projects like the Square Kilometre Array are racing to detect even the faintest whisper from this time, pushing technology to its limits. Succeed, and we could witness the universe's transformation from smooth simplicity to intricate complexity, a metamorphosis hidden until now. But perhaps the most humbling thought is this: the Dark Ages aren't just a distant memory. They're still out there, etched into the fabric of space itself. The light from that era hasn't vanished, it's been stretched, redshifted, diluted into near nothingness, but it exists. With the right tools and patience, we might one day decode it, turning the universe's greatest silence into its most revealing chorus. Until then, this frontier remains a blank space on the map, a reminder of how much we have yet to see, and how extraordinary the cosmos was even in the dark. Even in the deepest darkness of the cosmic dark ages, the universe wasn't truly empty, it was crackling with quantum potential. At scales smaller than an atom, particles flickered in and out of existence, governed by the strange rules of quantum mechanics. These fleeting fluctuations might seem insignificant, but they held the blueprint for everything we see today. How? Because in the first trillionth of a second after the Big Bang, those microscopic quantum ripples were stretched across the cosmos by a runaway expansion called inflation, magnifying them into the faint density variations that gravity would later sculpt into galaxies. Think of it like blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, the dots don't just spread apart, the space between them stretches too. Now imagine those dots are quantum fluctuations, and the balloon is the entire universe, expanding faster than light itself during inflation. What began as subatomic wobbles became cosmic-scale wrinkles, regions where matter was ever so slightly denser or sparser than average. These imperfections were tiny variations of just one part in 100,000, but they were enough. Gravity, acting over hundreds of millions of years, seized on these differences, pulling gas into the denser regions and leaving the emptier ones to become vast cosmic voids. Here's where quantum mechanics defies intuition. These fluctuations weren't caused by anything we'd recognize as a physical process. No collisions, no explosions. Instead, they arose from Heisenberg's uncertainty principle, which states that even in a perfect vacuum, energy can't be precisely zero. At the quantum level, particles and fields are constantly jittering, borrowing energy from the future to exist momentarily before vanishing again. During inflation, this quantum fuzziness got locked into the fabric of spacetime, frozen into the distribution of matter like a fingerprint pressed into wet clay. The wildest part, we can see this quantum signature today. The cosmic microwave background, the afterglow of the Big Bang, displays those same density variations as slight temperature differences, hotter spots where matter was denser, cooler spots where it was thinner. It's as if the universe preserved a photograph of its own quantum origins, a snapshot of randomness amplified into structure. And without those initial quantum seeds, the dark ages might never have ended. Gravity would have had nothing to grip, leaving the cosmos a featureless sea of gas. But quantum fluctuations didn't just dictate where structure formed, they also shaped how it formed. Recent simulations suggest that the precise spectrum of these variations, how many large versus small wrinkles there were, determined whether the first stars clustered tightly or scattered sparsely. Some theories even propose that alternate quantum rules could have produced a universe with no galaxies at all, just a smooth, sterile expanse. Our cosmos got lucky. Its quantum roll of the dice produced just enough variation for complexity to emerge, but not so much that matter collapsed into black holes before stars could ignite. This quantum legacy isn't just ancient history. Every galaxy, every star, every planet carries these primordial fluctuations in its DNA. The Milky Way's spiral arms, the voids between superclusters, even the distribution of galaxies across the sky, all trace back to those quantum tremors in the first moments of time. It's a staggering thought. The same physics that governs electrons in a lab today also wrote the blueprint for the cosmic web. And as we peer deeper into the dark ages, we're not just studying the past, we're deciphering the quantum code that built reality itself. The silence of the cosmic dark ages couldn't last forever. Deep within those vast, invisible clouds of hydrogen, pressure was building literally. As gravity pulled gas into ever denser knots, temperatures soared to millions of degrees, forging furnaces so intense they could overcome the universe's stubborn neutrality. The first stars didn't just flicker on, they erupted, flooding the cosmos with radiation so energetic it could strip electrons from atoms in a process called reionization. Picture trillions of tiny lights switching on across a pitch-black continent, each one burning away the fog around it. This wasn't just illumination, it was a revolution. What made these first stars so transformative wasn't just their light, but their violence. Unlike modern stars, which often live for billions of years, these pioneers were colossal and short-lived, exploding as supernova within mere millions. Their deaths seeded the universe with heavier elements: carbon, oxygen, silicon, the raw materials for future stars, planets, and life. But their most profound impact came from their ultraviolet radiation, which acted like a cosmic scalpel, slicing through neutral hydrogen and splitting atoms back into protons and electrons. This process didn't happen evenly. Early galaxies became beacons, their radiation carving bubble-like zones of ionized gas that expanded and merged over time like thawing ice sheets in spring. Here's where the story gets messy. Reionization wasn't a single event, it was a chaotic stop-start cascade. Some regions of the universe ionized early, while others clung to their neutral hydrogen for hundreds of millions of years. Quasars, the blazing cores of distant galaxies powered by supermassive black holes, added to the turmoil, their jets punching holes through the remaining fog. Yet even as light triumphed, it left clues. The way hydrogen absorbed certain wavelengths from quasars reveals patches of lingering neutrality, like shadows cast by the last remnants of the dark ages. The end of this era didn't just change the universe's appearance, it changed its very nature. Ionized hydrogen, being electrically charged, could now interact with magnetic fields and cosmic rays, altering how galaxies formed and evolved. The universe became transparent to ultraviolet light, allowing radiation to travel freely and shaping the environments where future stars would ignite. And perhaps most remarkably, that transition wasn't instantaneous, it's still unfolding in the farthest reaches of space, where the last pockets of neutral hydrogen are only now being breached by the advancing frontier of starlight. We're witnessing echoes of this epoch today. When astronomers study the most distant quasars, they're seeing snapshots of reionization in progress, their light filtered through gas in various states of ionization. The James Webb Space Telescope is now capturing galaxies from this pivotal era, their young stars still surrounded by the fading mist of the dark ages. It's as if we're watching the universe wake up in real time, one brilliant, explosive dawn at a time. The epoch of reionization was the universe's great awakening, a turbulent period when the first starlight didn't just pierce the darkness but fundamentally reshaped the cosmos. Think of it as a cosmic renaissance where the bland, neutral hydrogen fog that had dominated space for hundreds of millions of years was suddenly set ablaze with radiation. This wasn't a gentle transition, it was a violent metamorphosis driven by the relentless ultraviolet glow of newborn stars and quasars. Their intense energy acted like a cosmic blowtorch, splitting neutral hydrogen atoms back into protons and electrons, a process called ionization. For the first time since the Big Bang's afterglow faded, light could travel freely across vast distances, etching the universe with structure and possibility. What made reionization so pivotal wasn't just the return of light, it was the way it transformed the very fabric of space. Before this era, neutral hydrogen absorbed most ultraviolet radiation, trapping it like a thick blanket. But as stars and galaxies multiplied, their collective UV output began punching holes in that blanket, creating ever-expanding bubbles of ionized gas. Over hundreds of millions of years, these bubbles overlapped and merged like thawing ice giving way to open water. The universe didn't reionize all at once. It happened in patches, with some regions blazing clear early on while others clung to their neutral hydrogen for eons. The architects of this transformation weren't just any stars, they were behemoths. The first generations burned hot and fast, their ultraviolet radiation far more intense than modern stars. Many exploded as supernova within a few million years, scattering heavy elements into space while their surviving siblings kept flooding the cosmos with ionizing energy. Quasars, the luminous cores of distant galaxies powered by voracious black holes, added to the chaos, their jets carving vast tunnels through the remaining hydrogen fog. Together, they turned the universe into a mosaic of light and shadow, with ionized zones glowing like embers in the dark. Yet reionization wasn't just about destruction, it was about liberation. By stripping electrons from hydrogen, it changed how matter interacted with light and magnetic fields, setting new rules for galaxy formation. Ionized gas could no longer cool as efficiently, altering the way stars clustered and grew. The universe became transparent to certain wavelengths, allowing distant starlight to reach across cosmic distances for the first time. This shift was so profound that today, when astronomers study the farthest quasars, they're effectively looking back at reionization in progress, their light tinged red as it passes through the last wisps of neutral hydrogen on its way to us. The echoes of this era linger in the cosmic microwave background, where subtle polarization patterns hint at how and when reionization unfolded. Recent observations suggest it may have started earlier than we once thought, with pockets of ionization flickering to life barely 200 million years after the Big Bang. But the full story remains unfinished. Telescopes like JWST are now spotting galaxies from this pivotal epoch, their faint starlight helping us piece together how the universe emerged from its long, silent night. One thing is certain, without reionization, the cosmos would still be a featureless void, no glittering galaxies, no planets, no us. It was the moment the universe truly came alive. When the cosmic dark ages finally ended, they didn't just fade away, they were obliterated by the birth of the universe's first true stars, known to astronomers as Population 3. These weren't just bigger versions of the stars we see today. They were unlike anything that exists now, colossal infernos hundreds of times more massive than our Sun, burning at temperatures so extreme they could fuse hydrogen into helium in mere seconds. Picture a star so luminous its ultraviolet radiation could strip atoms apart light years away, its core churning with pressures modern stars will never experience. These were the cosmic pioneers that shattered the darkness, and their existence was as brief as it was spectacular. What made Population 3 stars so unique was their purity. Born from nothing but hydrogen and helium, the only elements available after the Big Bang, they lacked the heavier atoms like carbon or oxygen that help modern gas clouds cool and fragment. Without these cosmic impurities, early star-forming regions couldn't break apart easily, forcing gas to collapse into a single, monstrous star instead of a cluster of smaller ones. Simulations suggest some may have grown to 1,000 solar masses, dwarfing even the largest stars we observe today. Their sheer size meant they lived fast and died young, burning through their fuel in just a few million years before exploding as supernova or collapsing directly into black holes. But their power wasn't just in their brilliance, it was in their chemistry. When these giants exploded, they spewed the first heavy elements into the void, seeding the cosmos with carbon, nitrogen, and oxygen. For the first time, the universe had more than just hydrogen and helium. It had the building blocks for rocky planets, complex molecules, and eventually life itself. This was the moment the periodic table began to grow, and each new generation of stars inherited a richer palette of elements to work with. Their light also played a crucial role in reionization, tearing apart the neutral hydrogen that had dominated the dark ages. Unlike the gentle glow of modern stars, population 3 stars emitted torrents of high-energy ultraviolet radiation, capable of stripping electrons from atoms across vast distances. Wherever these stars ignited, they carved bubbles of ionized gas in the cosmic fog, like lighthouses piercing a global storm. Over time, these bubbles merged, transforming the universe from an opaque sea of neutral gas into the transparent cosmos we know today. Yet for all their importance, we've never directly observed a population 3 star. Their lifetimes were too short, their era too distant. The closest we've come is spotting the chemical fingerprints they left behind ancient galaxies with traces of primordial elements, or distant quasars whose light passed through clouds enriched by early supernova. Some theories even suggest a few might still linger in the universe's remotest corners, though finding them would be like spotting a single candle in a desert. What's certain is that their legacy is everywhere. The iron in our blood, the calcium in our bones, the silicon in Earth's crust, all were forged in the hearts of stars, and the very first to contribute were these dazzling, short-lived giants. They didn't just end the dark ages, they set the stage for everything that followed, from the birth of galaxies to the rise of life. And though they vanished billions of years ago, their light still echoes through the cosmos, a faint but indelible signature of the moment the universe first truly awoke. The deaths of the first stars weren't just final acts, they were cosmic alchemy on a scale we can barely fathom. When those colossal population 3 stars reached the end of their brief, brilliant lives, they didn't fade quietly. They erupted in supernova so violent they could outshine entire galaxies, scattering their guts across the void in a firestorm of creation. This wasn't mere destruction, it was the universe's first act of recycling, forging the very elements that would make planets, oceans, and life possible. At the heart of these explosions, temperatures soared to billions of degrees, conditions so extreme they could fuse atoms into forms hydrogen and helium alone could never achieve. In mere seconds, nuclear reactions churned out carbon, oxygen, neon, even iron elements that had never existed before. These weren't just trace amounts. A single supernova could blast forth the mass of 1,000 suns in heavy elements, seeding its surroundings like a gardener scattering fertile soil. Over time, these enriched clouds became the raw material for new stars, each generation inheriting a richer chemical palette than the last. The echoes of this process are all around us. The iron in our blood, the calcium in our bones, even the silicon in Earth's crust, all were forged in the hearts of dying stars. But those first supernovae were special. Unlike modern explosions, which often leave behind neutron stars or black holes, the earliest ones might have been so powerful they vaporized themselves completely in what's called a pair instability supernova. No remnant, no debris, just a shockwave of pure creation rippling through the cosmos. these explosions did more than spread elements, they shaped the future of star formation itself. Heavy atoms act like cosmic refrigerants, helping gas clouds cool and collapse into dense knots that birth new stars. Without that first seeding, galaxies might have remained barren, their gas too warm and diffused to fragment efficiently. It's a staggering feedback loop. Stars create elements, elements enable more stars, and so on, building complexity over billions of years. Yet the legacy of those first supernovae isn't just in what they made, it's in what they destroyed. Their ultraviolet radiation and shockwaves ripped through nearby gas clouds, heating them, shredding them, sometimes triggering new waves of star formation elsewhere. They carved the first bubbles in the cosmic web, creating the patchwork of voids and filaments we see today. And when their debris finally settled, it didn't just enrich the universe, it diversified it, creating pockets with slightly different chemical mixes, setting the stage for the planetary diversity we now take for granted. We're still finding traces of this ancient pollution today. In the atmospheres of the oldest stars, astronomers detect barely a sprinkle of heavy elements, relics of that first seeding. Some distant gas clouds show chemical signatures that can only come from single, extraordinarily massive supernova, time capsules from an era when stars died young and left everything behind. Even our solar system carries the imprint. Isotopic ratios in meteorites suggest our Sun formed from gas enriched by multiple generations of stellar explosions, a heritage written in stone. What's most remarkable is how delicate this balance was. Too few supernovae and the universe would have remained a hydrogen desert. Too many, and radiation might have sterilized entire galaxies. Instead, those first cataclysms struck a perfect middle ground, transforming the cosmos from a monotonous void into a chemical playground ripe for complexity. The explosions that ended the Dark Ages didn't just light up the universe, they gave it the tools to build itself anew, over and over, until finally, against all odds, it built us. Among the first generation of stars, the most massive didn't just fade away, they may have collapsed into the very first black holes, seeding the cosmos with gravitational monsters that would shape galaxies for billions of years. Picture a star so enormous its core couldn't even explode as a supernova. Instead, it imploded under its own weight, vanishing from the visible universe and leaving behind a singularity so dense not even light could escape. These weren't the supermassive black holes we see at galactic centers today, but their primordial ancestors, tiny by comparison yet unimaginably influential. The process would have been terrifyingly simple. For stars more than about 250 times the mass of our Sun, the heat in their cores became so intense that photons spontaneously transformed into electron-positron pairs. This robbed the star of the radiation pressure holding it up, triggering a catastrophic collapse. No shockwave, no brilliant explosion, just a sudden, silent collapse straight into a black hole. Unlike modern supernova, which fling heavy elements across space, these stars may have left almost no chemical traces, swallowing most of their mass whole. But gravity never forgets. These black holes, some just a few dozen times the Sun's mass, became gravitational anchors in the early universe. As they sank toward the centers of protogalaxies, their gravity attracted gas, dark matter, and even other black holes. Simulations show how these primordial seeds could have merged over time, growing through violent collisions and relentless accretion. Every time two black holes spiraled together, they released ripples in space-time gravitational waves that we're only now learning to detect. Some may have grown rapidly, gorging on the dense gas of the early universe to become the intermediate mass black holes we still struggle to explain today. Others could have been flung into intergalactic space by gravitational slingshots, becoming invisible wanderers in the cosmic dark. But the most intriguing possibility is that these first black holes laid the groundwork for the supermassive monsters we see today. The same halos of dark matter that birthed the earliest stars also funneled gas toward their centers, creating ideal feeding grounds for growing black holes. Some may have snowballed in size, merging with rivals and consuming entire stars to become the billion solar mass behemoths that power quasars by the universe's first billion years. It's a puzzle we're still piecing together, how something so small could grow so large, so fast, without leaving obvious traces of its youth. What's certain is that these objects transformed their surroundings. As they fed, their radiation and jets heated nearby gas, stifling star formation in some regions while triggering it in others. Their gravity sculpted the orbits of stars, creating the dense nuclei we see in modern galaxies. And their mergers, detectable across billions of light years, now serve as cosmic laboratories for testing Einstein's theories. The irony is profound. The darkest objects in existence may have been the spark that lit the universe's brightest beacons. Yet for all their power, the first black holes remain elusive. Their starlight is long gone, their growth obscured by time. Only now, with gravitational wave detectors and telescopes peering back to the cosmic dawn, are we catching glimpses of their legacy. Some may still exist nearly unchanged, drifting in galactic halos or lurking unnoticed in star clusters, ghosts of a time when the universe was young, violent, and unimaginably strange. Their story isn't just about destruction, it's about how the darkest corners of reality helped build the cosmos we know today. When the first galaxies began to coalesce from the chaos of the early universe, they didn't form in the majestic spirals or elegant ellipticals we recognize today. Instead, they emerged as messy, misshapen blobs, clusters of young stars and gas clinging together in the gravitational embrace of dark matter. These were the universe's first cities, built not from steel and stone, but from the raw materials left behind by the earliest supernova. Picture a cosmic construction site where gravity was the foreman, gathering hydrogen and helium into sprawling, unstable structures that flickered to life with the glow of countless newborn stars. The process wasn't quick or orderly. After the first stars ignited, their explosions scattered heavy elements like cosmic fertilizer, enriching the surrounding gas with carbon, oxygen, and silicon. These new ingredients acted as coolants, allowing gas clouds to shed heat and collapse more efficiently than ever before. Dark matter, invisible but omnipresent, provided the scaffolding, its gravitational pull funneling gas into denser and denser knots. Over millions of years, these knots grew into protogalaxies, small, turbulent collections of stars and gas, each no larger than a fraction of our Milky Way, but teeming with activity. What's astonishing is how fragile these early galaxies were. Without the stabilizing influence of heavier elements and magnetic fields, they were prone to violent bursts of star formation, their gas reservoirs rapidly depleting in fiery outbursts. Some may have burned too bright too fast, blasting themselves apart with supernova before they could grow. Others merged in chaotic collisions, their stars and gas tossed into new configurations by the gravitational chaos. These weren't the stately cosmic islands we see today. They were dynamic, unstable, and constantly evolving. Yet within this turbulence lay the seeds of structure. The largest protogalaxies grew by cannibalizing their smaller neighbors, their dark matter halos merging into ever larger structures. Gas flowing along the filaments of the cosmic web fed their growth, while supermassive black holes born from the remnants of the first stars began to stir at their centers. Over time, these chaotic blobs settled into more stable shapes, their rotations smoothing into disks or their stars dispersing into swarms. The legacy of this era is written across the night sky. When we look at distant galaxies through telescopes like Hubble or JWST, we're glimpsing snapshots of this formative period, some caught in the act of merging, others shrouded in the thick dust of their star-forming frenzy. Their light, stretched by billions of years of cosmic expansion, carries the fingerprints of their youth, telltale signatures of rapid star birth, supernova debris, and the first stirrings of black holes. But perhaps the most remarkable thing about these early galaxies is how they transformed the universe yet again. Their collective starlight flooded the cosmos with radiation, completing the process of reionization and burning away the last remnants of neutral hydrogen. They forged the heavy elements that would one day form planets and life, and they set the stage for the universe we inhabit, a vast, interconnected web of galaxies, each carrying the echoes of that primordial dawn. The story of galaxy formation isn't just about the past, it's about the ongoing evolution of the cosmos. Every galaxy we see, including our own, is the product of billions of years of growth, collision, and transformation. And as we peer deeper into space, we're not just observing distant objects, we're uncovering the blueprint of our own origins, written in starlight and gravity. The James Webb Space Telescope isn't just another observatory, it's a time machine, engineered to capture the faintest whispers of light from the universe's darkest chapter. Peering into the cosmic dark ages is like trying to read a book with half its pages ripped out. But Webb's infrared eyes are designed to detect the very signals other telescopes miss. While Hubble gave us breathtaking views of galaxies a few 100 million years after the Big Bang, Webb pushes further, hunting for the first flickers of starlight that ended the dark ages altogether. Its instruments are so sensitive they can pick up the thermal glow of a bumblebee on the moon, making it the perfect tool to spot the dim, redshifted signatures of primordial galaxies hiding in the void. What makes Webb revolutionary isn't just its power, it's its strategy. The Dark Ages left no visible light to study, but as the universe expanded, the ultraviolet radiation from the first stars stretched into infrared wavelengths. Webb's mirrors and sensors are fine-tuned to catch this stretched light, effectively turning invisible history into detectable data. Already, it's spotted galaxies from shockingly early times, some so mature and massive they've upended theories about how quickly structure formed. These discoveries suggest the Dark Ages might have ended sooner and more dramatically than we thought, with galaxies igniting in a cosmic flash mob rather than a slow procession. But Webb isn't working alone. Ground-based radio telescopes like the Square Kilometre Array are hunting for the 21-centimetre line, a faint radio signal emitted by neutral hydrogen during the Dark Ages. While Webb sees the aftermath, SKA aims to map the darkness itself, charting how hydrogen's distribution shifted as the first stars ionized it. Together, these instruments form a complementary toolkit, one capturing the end of the era, the other its middle act. It's like reconstructing a lost civilization by studying both its ruins and the soil layers beneath them. The data pouring in is rewriting textbooks. For decades, we assumed the first galaxies were small and fragile, but Webb's snapshots reveal sprawling, dusty systems brimming with stars, hinting that star formation might have begun earlier and in greater quantities than models predicted. Some galaxies even show signs of supermassive black holes at their cores, raising questions about how these monsters grew so fast. Did they form directly from collapsing gas clouds, leapfrogging the star stage entirely? Or were the first stars so massive their deaths birthed black hole seeds of unprecedented size? Every new image from Webb feels like uncovering another piece of a puzzle we didn't know existed. Yet challenges remain. The farther back we look, the scarcer photons become, and the harder it is to distinguish true primordial galaxies from imposters, later galaxies masquerading as early ones due to dust or distance miscalibrations. Scientists are racing to confirm these sightings with spectroscopic analysis, splitting the light into rainbows that reveal chemical compositions and redshifts with precision. Already, teams have identified galaxies dating to just 250 million years after the Big Bang, their light bearing the unmistakable signature of youthful stars with almost no heavy elements. These are likely some of the universe's first island cities, their glow finally reaching us after a 13 billion-year journey, the ultimate goal. To catch a galaxy in the act of emerging from the dark ages, a system so young its stars are still surrounded by the neutral hydrogen fog they're actively burning away. Such a discovery would be the Rosetta Stone of cosmic dawn, showing us the exact moment the universe transitioned from darkness to light. And with Webb's projected 20-year lifespan, plus upcoming missions like the Roman Space Telescope and Louvre, we're closer than ever to watching that transformation play out in real time. This isn't just about satisfying curiosity. Understanding the Dark Ages reveals how ordinary matter triumphed over darkness to build the galaxies we see today, and how delicate that balance was. Tweak the timing of reionization, alter the efficiency of star formation, or change the behavior of dark matter, and the universe might have ended up sterile and empty. Each new observation is a clue to why we exist at all, written in the fading light of the cosmos' first dawn. The hunt to unravel the cosmic dark ages is accelerating, with a new generation of telescopes and missions poised to crack open this enigmatic chapter like never before. While the James Webb Space Telescope has already shattered expectations by spotting galaxies from shockingly early times, even more revolutionary tools are on the horizon, instruments that won't just glimpse the aftermath of the Dark Ages, but may finally penetrate the darkness itself. Imagine radio arrays so vast they span continents, space observatories chilled to near absolute zero, and gravitational wave detectors sensitive enough to hear the echoes of primordial black holes. This isn't just incremental progress, it's a full-scale assault on one of cosmology's last great frontiers. At the forefront is the Square Kilometre Array, a sprawling network of radio antennas across South Africa and Australia that will become the most sensitive radio telescope ever built. Unlike optical telescopes that rely on light, the SKA is designed to detect the faint 21-centimeter signal emitted by neutral hydrogen during the Dark Ages, a whisper from the era before stars. By mapping how this signal varies across the sky, scientists could reconstruct the universe's structure during its darkest phase, revealing how gas flowed into the gravitational wells of dark matter and pinpointing the exact moments when starlight began tearing through the fog. Early prototypes have already hinted at unexplained anomalies, like potential interactions between dark matter and hydrogen that could rewrite our understanding of fundamental physics. Meanwhile, NASA's upcoming SPHEREX mission will scan the entire sky in infrared, hunting for the faint glow of the first galaxies as they burned away the cosmic haze. Unlike Webb, which focuses on deep but narrow fields, SPHEREX will provide a panoramic view of reionization's progression, showing where and when bubbles of ionized gas first emerged. Its data could settle fierce debates about whether reionization was driven primarily by massive stars or quasars, or some exotic process we haven't even considered. And then there's the European Space Agency's LISA mission, a space-based gravitational wave observatory that might detect mergers of those elusive first black holes, offering clues about how they grew so rapidly after the Dark Ages ended. But perhaps the most daring ideas involve reaching even further back, to the Dark Age equivalent of the cosmic microwave background. Projects like NASA's Lunar Crater Radio Telescope propose building a kilometer-wide radio dish on the far side of the Moon, shielded from Earth's interference, to capture ultra-low-frequency radio waves from the universe's first atoms. These signals, redshifted beyond detection by any Earth-based instrument, could reveal the moment when hydrogen atoms first formed after the Big Bang, bridging the gap between the CMB and the Dark Ages. It's a long shot, but success would give us a continuous timeline from creation to cosmic dawn. Theoretical breakthroughs are advancing just as rapidly. New simulations fueled by exascale supercomputers now model the Dark Ages with unprecedented resolution, tracking not just gas and dark matter, but magnetic fields, turbulence, and even the quantum effects that might have influenced star formation. Some models suggest that exotic particles like actions could have subtly altered how gas cooled, while others explore whether primordial black holes, tiny relics from the Big Bang, might have jump-started galaxy formation. Every tweak to these virtual universes offers testable predictions for upcoming observatories, turning simulations into a playground for discovery. What makes this era of exploration so thrilling is how collaborative it's become. Radio astronomers, infrared specialists, gravitational wave hunters, and theorists are now pooling data like never before, each perspective filling gaps in the others. When SKA detects the 21-centimeter signal, Webb can zoom in on the galaxies responsible. When LISA hears a black hole merger, simulations can trace its lineage back to the first stars. Together, they're weaving a narrative of how darkness gave way to light and how a lifeless void became a universe capable of asking questions about itself. The ultimate goal, to witness the cosmic dark ages not as a blurry gap in our timeline, but as a dynamic, transformative epoch with its own rhythms and turning points. With luck, within our lifetimes, we'll have maps of hydrogen clouds from 13 billion years ago, movies of reionization bubbling across space, and maybe even proof of phenomena we've never imagined. Because when it comes to the universe's first chapters, every answer we uncover seems to reveal even deeper questions, and that's what makes the hunt so endlessly compelling. The cosmic dark ages force us to confront a humbling truth. We are the products of an unimaginable chain of cosmic accidents, each link as fragile as it was necessary. For billions of years, the universe existed without a single witness, its silent evolution governed by laws indifferent to life or consciousness. That we now trace its history, that atoms forged in those first chaotic stars now assemble into minds capable of deciphering their own origins, is nothing short of miraculous. This era reminds us that existence isn't a given. It's a fragile exception carved out of darkness by forces we're only beginning to understand. There's a profound irony in how we study this period. The same tools we use to probe the Dark Ages, telescopes, supercomputers, equations, are made possible by the very elements those ancient stars created. We are, in a very literal sense, the universe studying itself, a loop of self-awareness that began when the first photons tore through the void. It raises questions that straddle science and philosophy. Would a universe without observers still have meaning? Does our ability to comprehend the cosmos imply it was somehow meant to be comprehended? Or is this just one of countless possible outcomes in a multiverse where most realities remain forever dark? What's equally striking is how contingent everything appears. The Dark Ages weren't preordained, they were the result of specific, finely tuned physics. If the density fluctuations from inflation had been slightly weaker, gas might never have collapsed into stars. If dark matter behaved differently, galaxies could have formed too slowly or too fast. Even the molecular chemistry of hydrogen, subtle as it was, had to strike a perfect balance to allow cooling without excessive fragmentation. The fact that these variables align to create a universe rich with galaxies, planets, and life suggests either an astonishingly improbable roll of cosmic dice or a deeper principle we've yet to uncover. This era also reshapes our understanding of time. The Dark Ages spanned hundreds of millions of years, longer than all of human civilization, compressed into a single breath of cosmic history. Yet from our vantage point, we compress those eons into paragraphs, treating them as a prelude to the real story of stars and galaxies. But what if we're the footnote? The universe spent far longer in darkness than it has in light, and it may one day return to darkness as expansion tears galaxies apart and stars fade. Our luminous epoch could be just a brief spark between eternities of shadow, a thought that's either terrifying or oddly comforting, depending on how you frame it. Perhaps the deepest lesson lies in the Dark Ages' very invisibility. For most of human history, we had no idea this era existed. The night sky seemed eternal, its stars unchanging. Only through painstaking detective work, Decoding microwaves, simulating universes, chasing spectral whispers, did we uncover this hidden chapter? It's a reminder that reality extends far beyond what we perceive, and that the answers to our biggest questions often lurk in the gaps between what we can see. The universe's greatest stories might still be hiding in plain sight, waiting for the right tools, the right minds to bring them into the light. In the end, studying this epoch isn't just about reconstructing the past, it's about redefining what's possible. A universe that could emerge from absolute darkness to create planets, life, and meaning hints at capacities we're only beginning to grasp. If gravity and gas could turn emptiness into complexity once, what other transformations might still lie ahead? The cosmic dark ages don't just tell us where we came from, they invite us to imagine where we and the universe might go next. From the infinite silence of the cosmic dark ages to the dazzling brilliance of today's universe, we've traced an epic journey, one that began with a featureless void and ended with galaxies, planets, and even us. It's a story of transformation so profound it defies imagination. How the simplest ingredients, hydrogen, helium, and the invisible pull of dark matter combined in just the right ways to ignite the first stars, forge the first heavy elements, and set the stage for everything that followed. This wasn't just a change in the cosmos, it was a revolution, a moment when darkness surrendered to light in a way that made life possible. Think about the sheer improbability of it all. The universe could have remained forever dark, its gas too diffused to collapse, its stars stillborn. Instead, gravity's patience and quantum physics quirks conspired to create the conditions for light to emerge. Those first stars weren't just beacons, they were alchemists, turning hydrogen into the building blocks of planets and life. Their explosions seeded the cosmos with carbon, oxygen, and iron, while their radiation burned away the cosmic fog, sculpting the transparent universe we now peer into with our telescopes. This story isn't just about the past, it's unfolding right now. Every star you see in the night sky owes its existence to those primordial giants. Every atom in your body was forged in the heart of a star that lived and died long before our solar system formed. We are quite literally the universe's way of understanding itself, the result of 13 billion years of cosmic evolution, and the most astonishing part. We're only beginning to uncover the details. With each new telescope, simulation, and discovery, we peel back another layer of this ancient mystery, revealing just how interconnected our existence is with the cosmos' earliest moments. Yet for all we've learned, the Dark Ages still hold secrets. How exactly did the first black holes form? Were there stars even earlier than we've detected? Could pockets of pristine hydrogen from that era still linger, untouched by starlight? These questions aren't just academic, they're clues to understanding the universe's deepest workings and perhaps even our place within it. So as we close this chapter, remember, the night sky isn't just a static backdrop. It's a living chronicle, a record of that extraordinary transition from darkness to light. Every time you look up, you're seeing the legacy of that cosmic dawn, a story still being written, still waiting for us to explore. The universe didn't just wake up once. It keeps unfolding, revealing new wonders to those who dare to keep searching. And who knows, the next great discovery might be just one observation away.